Good morning, everyone. So far in this class, we've been spending time talking about how buildings work, and specifically how steel structures work. We looked at how the framing in the floor system and the columns that support the floors are arranged to support gravity loads. For a uniform load, we trace through what the load might be on a joist, which is supported by the girder. So we trace the load through the joist and find out what the load might be on the girder. And then we trace the load through the joists and the girders that are framed into the column to figure out what the load on the column might be at each floor. And then in lectures 5 and 6, we talked about the types of gravity loads. How do we figure out what the uniform load is that we're actually getting these loads for? We talked about dead, live, and snow loads. Generally, take them as uniformly distributed in the sense that they're going to generate maximum actions that we expect our structure to see during its life. We talked about braced frame systems and how we might experience lateral forces from wind, from earthquake shaking, and there's also a destabilizing effect from gravity loads that we consider through this application of an imaginary load called notional lateral loads. And so we kind of understand, or at least we've explored, the types of loads acting on structures, how those loads work their way through the structure, so we might be able to get the bending moment on a joist from dead, live, or snow, the axial force on a brace from wind, earthquake, and also from the effects of the gravity loads present in the structure. So basically, we spent a lot of time talking about the materials we don't really understand and molding them into shapes we can't really analyze to withstand forces we cannot really assess in such a way that the public doesn't really suspect. And basically what's going on here is we need to assess loads. We need to calculate something. We know that those loads are going to have effects on structural members. And as long as the structural members don't fail, the public's not even going to know that this is the kind of stuff that we're up to, right? No one's thinking about, gee, I really hope that, Taylor calculated the wind load using a 1 in 50-year return period and factored them up appropriately and made sure that the brace was strong enough to take that force. No one's thinking that when they're in a structure. So that's kind of what this last little piece means. What we're going to start talking about today is how we do this in such a way that the public doesn't really suspect, right? We want our structures to withstand these forces we can't really assess. How do we add the effects of the different forces that we've talked about so far in this course together so that when we're sizing the members later on in the course, we know that we're making sure that they're sufficiently strong to withstand forces that are exceptionally rare so that we don't experience any failure. I've shown this slide a couple times, and I've talked about both of these things a little bit. We've really spent most of our time talking about part 4 of the building code to get dead, live, snow, wind, and earthquake loads. We talked about how to perform structural analysis, mostly by hand, but we're also going to be using STAAD.Pro in this course. And the rest of the course is basically going to be the right-hand side of this slide, where we're going to start talking about the resistance of different steel members in accordance with the steel standard. I've already talked a little bit, though, about structural steel, and we explored, for instance, what the variability might be in the estimated resistance of a member in tension, for example, and we looked a little bit about what the variability might be around the loads that we're trying to calculate. Okay, and so today we're going to introduce what these two curves mean, what happens when those two curves overlap, and basically we're going to assess that through something called structural reliability. Reliability means you expect something to do something or perform a certain way indefinitely or for a long period of time. A reliable structure is a structure that stands for the life of the structure. Okay, and so we're going to talk about how we get a reliable structure and how we make sure the probability of failure is acceptably small. And that's going to transition us into this design approach that we follow called limit states design. Limit states design is basically a way of separating out failures that are catastrophic, that we never want to have happen, from failures that are just annoying to people using the structures, and we can accept them every once in a while. As we mentioned, what the hell is this? Oh, there we go. As I mentioned the other day, right, we went through a very quick example of maybe trying to calculate what we might expect the yield load for a set of double angles might be. And we said it's probably going to be 875 kilonewtons based on the specified area in the handbook and the specified yield strength for the structural steel that we're using. But if you measure that load a bunch of different times, you'd expect to get a variability around that estimated value. And we have a certain probability that we're actually overestimating the strength. We don't want to overestimate the strength, especially if we're underestimating the load. We have loads like dead and live loads. We didn't look at load statistics for wind or snow or earthquake, but this is enough to make the point that I'm going to be making today. Live loads we tend to underestimate or overestimate, but the variability is quite large, and so it's just as likely that we'll have a live load that's bigger than we expected, whereas for dead loads we tend to overestimate them, and there's less variability. And so we tend to estimate the dead load to be this. It might be something out here, whereas we tend to estimate the live loads to be something like this. It could be anything within the range of the probability distribution function. So our goal today is to figure out how often are we actually underestimating the loads, how often are we actually overestimating the strength, and how do we make sure those two things don't happen together at the same time with an acceptably small probability. Okay, so basically after today, you should be able to discuss the statistical principles. Again, I use that term lightly, used to provide structural reliability and calculate something called a reliability index or a margin of safety. Should be able to define, describe, and differentiate between what we call ultimate limit states and what we call serviceability limit states and how they're going to apply to the design of steel structures. And find and apply the National Building Code load combinations to calculate factor load effects, primarily for ultimate limit states. ULS here is ultimate limit states. And from time to time in this course, we'll also look at serviceability limit states. Okay, does anyone have any questions about why these three things might be important for us before we get into the material this morning? Pardon me. So what is this limit states design? First, we need to know what limit states design is so we can understand why we're trying to do any kind of statistics to make sure we have a reliable structure. Limit state is basically something that happens to prevent the building from fulfilling its intended function. And that's kind of vague, and I don't know how to describe that. Basically, if something happens in a building and it's not doing its job anymore, can you think of something that might happen in a building so that it's not doing its job anymore? Poor construction. What does poor construction lead to, though? Poor construction is an action that leads to collapse, perhaps, right? A beam falls through the floor. That's not fulfilling its intended function. People are not intended to fall through the floor in structures. Snow is not intended to fall on your head if you're on the upper building. Buildings are not intended to fall over sideways in wind and earthquake loading. So the failure of a brace in tension, the buckling of a brace in compression, those are the kinds of things that might be things we don't want to have happen. But it also includes other things like floors that are too bouncy. You don't intend for people to kind of bounce along the floor. Has anyone walked to the engineering library since I talked about that, like the first week of class? You have to go walk. It's not the intended function of your building to be bouncing along the floor as you're walking across it. It's not the intended function for this wall to shift so much that we can't open the door during a fire escape. It's not the intended function of the walls to crack so that the windows don't open. There are things that the building is intended to do, which means keep people safe. People should be safe in the structures, but we should also be able to use them comfortably. And that's basically going to be the differentiation between ultimate limit states and serviceability limit states. Ultimate limit states are basically the limit states concerned with safety, and we're going to call them ultimate for no other better reason than, well, I don't know, ultimate limit state sounds cool, I guess. Basically, it includes anything where we're exceeding the load carrying capacity of a member, there's overturning or sliding or fracture of any particular components. What it means for us is we're going to want to prevent yielding that results in uncontrollable movement. We're going to want to prevent fracture of members or bolts or welds that connect everything together. We're going to want to prevent buckling of columns and beams. And we're going to want to prevent concrete from crushing. Obviously, our structure is ultimately going to be supported by some concrete foundations. We're not talking about the foundations per se, but we will talk about where the columns meet the foundations and how we can prevent that concrete from crushing underneath the structure. The objective here is to prevent these things from happening, and this is kind of where things get a little bit fuzzy for most people trying to describe what we do. We're trying to prevent that with a reasonable amount of certainty. We can never, ever make all of these things impossible. It's impossible to make it impossible. There's always a probability that something bad will happen. What is a reasonable amount of certainty? That's something we'll talk briefly about today. But basically, we want to prevent these things from happening so that we don't get undesirable failure mechanisms or anything that results in partial collapse or full collapse of our structures. Okay, so this reasonable amount of certainty is kind of an interesting point, and we're going to talk about that a little bit today. And so on the next slide here, I'm going to have a poll everywhere question just to get a sense for whether or not people might think certain things may or may not be reasonable. And so let's say I've got a column in the building and I'm standing under or next to the column, and I don't want the column to buckle so that it collapses on my head and kills me, right? That's a pretty reasonable thing to expect of a structure. We cannot make it impossible that that happens. What would be an acceptable probability that that failure might occur in a structure compared to any of these things happening? Shuffling a deck of cards into the same order twice, winning the lottery, dying by choking on your own food, a pregnancy with twins, or getting an A+ in this course. What is an acceptable probability in terms of comparing it to any of these 5 things? What is an acceptable probability that we're going to accept that a column might collapse, resulting in a building falling down and killing the person inside? I'm going to just check to make sure that it's actually active here, so give me 1 second, but that'll give you a few seconds to think about it before submitting an answer. Talk about it with your friends, call home and talk to someone who's still sleeping. Oh, it is active. Is it not working? That's weird. Because it says it's active, it may be locked for some reason. No, it says it's active. Let me deactivate it and I'll activate it again. Is it working? Really? Okay, so we'll do a workaround here. Maybe we'll just do a show of hands. Is it acceptable that people will die from a column buckling in terms of comparing that to probability of shuffling a deck of cards? How many think that the probability of shuffling a deck of cards into the same order twice is an acceptable probability that someone will die in a structure? Okay, we'll talk about what that means in a minute. How many of you think that it's the same as winning the lottery? Okay. How many of you think it's dying by choking on your own food? Okay. A pregnancy with twins, getting an A+ in the course. Sure. So these are actually in order of like least likely to most likely. And what I mean by that is shuffling a deck of cards into the same order twice has a probability of 1 in 10 to the power of 68, which is like a 1 with 68 zeros at the end. If you shuffle the deck of cards every day for your entire life and you live to be like 1,000 years old, it's very unlikely that you would shuffle a deck of cards into the same order twice. Okay, so that's like one of the most impossible things that can happen as much as we can quantify things with a certain level of probability. Winning the lottery, that's like 1 in 14 million or so. Dying by choking on your food, 1 in 3,000 people might die by choking on their own food, okay? Pregnancy with twins is 1 in 250, and on average, about 1 in 10 people get an A+ in this course, okay? So in terms of whether or not those things are acceptable or not, we'll kind of try and put a little bit of sense around it. For the most part, it's somewhere, I guess I can't write on the slide, but it's actually surprisingly close to dying by choking on your own food. Okay, it's pretty rare that you're going to die by choking on your own food. And so for the most part, you're a little bit less likely to die from being in a structure that has a serious problem with it. Okay, and that's kind of how statisticians or people developing building codes would try to justify that for us. How do we figure out what this means, and how do we make sure that that probability is about slightly less than probability that you'll choke and die by choking on your own food? Well, we have a load that we might be calculating, and this is actually the mean value of what the load might be, and we already know it has some distribution around it. It might be, on average, we expect it to be this value here, but it could be over here, it could be over here, and it's dictated by this probability distribution function. The resistance is most likely to be here, but it could be down here, and it could be over here. Basically what this is if we look at these two curves, we want to avoid overestimating the resistance, right? We're trying to calculate this, and we might get this, at the same time that we underestimate the strength, or the load effects. We're trying to calculate S and R. We want R to be bigger than S, but it's possible that S will be bigger than R sometimes. And basically what this means is every time we underestimate the loads and we overestimate the strength, we expect to get a failure happening, right? I think that makes sense. Every time we underestimate the load on the brace, and at the same time that we underestimate or overestimate the strength of the brace, and those two things happen at the same time, we're going to get failure in our structure. So basically what this means is this area here, where these two curves overlap, that represents the probability of failure. Where these two probability distribution functions overlap, that represents the probability that we're going to have failure in our structure. Okay, that's basically the probability that an improbably large load will be larger than an unlikely small R value. And so basically we can write this as that's the probability that S is going to exceed R, which means we're likely to get some kind of structural failure. Does anyone know how to calculate that probability? So I think in statistics class you add and subtract random variables in statistics class. You probably forget. I don't even remember if you do that in statistics class. Basically what we need to do here to figure out what this probability is, we're going to take the distribution here, R, and we're going to subtract S. What that's going to do is give us a new curve where the mean is going to be the mean of R minus the mean of S, and the standard deviation is going to be the square root of the sum of the standard deviations squared. That's how you subtract a random variable from another one. And now what we have as a problem is a situation where on the left-hand side of this axis, this represents the probability that R minus S, maybe I'll rewrite this, the probability that R minus S is less than 0. If R minus S is less than 0, what does that mean about the strength versus the load? If R is less than S, it means S is bigger than R, right? R minus S is less than 0 means that the load is bigger than resistance. And so this area here now represents the probability of failure. Does anyone remember how to calculate this probability? Look, we already kind of looked at something like this in lecture 2. What kind of problem is this in terms of statistics? Normal distribution, but it's a type of score, right? A, B, C, D, E, F, G, H, I, J, all the way to Z, a Z score. This is a Z score problem. The Z score is the measure of the number of standard deviations the mean is away from 0, or from the point that we're trying to estimate. In this class, we're going to call Z beta. And beta is just the absolute value of Z. Okay, so here we're defining a new term called the reliability index, beta. And it's basically just a Z score, a measure of the number of standard deviations the mean is away from having the load effects exceed the resistance. So if we think of this as a Z score, then we can go to the table and we can figure out what reliability index we might want to target. And the bigger the reliability index, the further away R is from S. A reliability index of 1 means that the probability we'll experience failure is about 16%, or 1 in 6.3. If we go to 2, that's about 2 in 2.3%, or 1 in 44. A beta of 3 is 1 in 741. A beta of 4 is 1 in 31,250. And 4.5 is 1 in about 300,000. Okay, so winning the lottery is 1 in 14 million. That's like a Z score of 6 or 7 or 8. Shuffling a deck of cards in the same order twice, I don't even know what beta that would be. But we're somewhere in structures, we tend to play within the range of 3 to 4.5. 3 to 3.5 is what we target for ductile failure mechanisms, or ones that have a certain amount of warning before a failure actually occurs. Ductile failure mechanisms, we tend to be working in 4 to 4.5. If there's little warning that a collapse is going to happen, we want to make sure that failures that occur with little warning are more rare than failures that occur with more warning. Okay, so sorry, ductile. So ductile means use a lot of movement, right? Steel is ductile. Think of a brace elongating. It's going to move a lot. You're going to see your structure move a lot, and that should indicate that you should get the hell out of the structure, right? So it would be like brittle, and we'll talk about what these mean later on, but fracture of a bolt. You cannot see the bolt about the fracture. It's going to develop some force, and it's going to fracture. There's not a lot of movement associated with that kind of failure, and I'll talk about some of those eventually today anyway. Okay, so that's a sense for the kinds of scores that we're working with here, and we tend to play more or less in this range of reliability index. Okay, so what this means is we want to make sure that the standard deviation, we have 4 standard deviations between failure and what we are actually calculating is going on. Are there any questions about that concept or what any of these beta values might mean in terms of their z-score and resulting probabilities before we continue? Okay, so what do we do with this? Well, we already said before, there's a probability, and I'm throwing these kind of back to slide 2. This is not the next one you'll see, but we have a reasonable probability that we're going to be overestimating the resistance. And so what we're going to do is we're going to factor down our estimate. We're going to say whatever our estimate is, let's say 875, well, we're going to factor that down by 0.9, and it might look something like that. And if it's possible that we're going to overestimate the loads, we're actually going to bump up whatever it is that we think we're calculating so that we're playing somewhere out in these ranges. Okay, we're calculating this solid red line, 1. It's possible that we're overestimating the dead loads, but there's not much variability, so we're going to increase the dead loads a little bit so that we're playing out in this range. Live loads we're likely to overestimate, but there's a very large variability, so we're still going to apply a healthy increase to whatever load it is that we calculate. Basically, we're going to be increasing the load effects with different factors. We're going to be reducing the resistance with a certain factor. And our goal here is to make sure that when we increase our estimates of load and reduce our estimates of resistance, this is what we're going to check. We're going to check that our reduced resistance is bigger than our increased loads. And we're going to do that in such a way that we get the target reliability index. Okay, so when we factor up the loads and reduce the resistance, we should have, when we subtract those 2 random variables, a reliability index that indicates the probability of failure is going to be an acceptable value. Okay, that's basically what's going on here. Our resistance factors are going to be called phi in this class. Load factors, we don't really see them called anything else, but they're traditionally called alpha. And these are going to be different load effects for dead, live, and snow, depending on how likely it is that we're going to be underestimating those load effects. So you don't have to pay much attention to this next slide. I just want to show it to you to give you a sense for what this calculation might look like. Basically, we're going to do the same thing. We're going to subtract the random variables. The problem is these random variables tend to be log normally distributed. They don't tend to be normally distributed. The logarithm of the values tends to be normally distributed. So that changes the math a little bit. Basically, if we have a relatively small variance, then we can estimate the mean as the log of the mean values and the standard deviation as the variance of the values. In that case, beta is still going to be the average of the subtraction of the random variables divided by the standard deviation of the random variables. But now we're dealing with the natural log of the means and the same values of variance instead of standard deviation squared. Basically what we end up with, if we look at the definition of beta, we're going to figure out basically what alpha and phi might need to be to target an acceptable reliability index. So for example, we might plug in a value here of 3.5 for beta. We've already talked about where delta R and delta S might come from. Delta S would be delta D plus delta L if we're adding live and dead loads together. Delta R is just the variance that comes from the geometry, the professionalism of the equation, and the variability around the strength that's provided. Okay, so basically we go through this calculation, we put in beta, we want to get something so that we can figure out if we put in beta, what do alpha and phi need to be? And part of the problem is here we have two unknowns and only one equation, and that's a difficult thing. So we have alpha, actually we could have several unknowns. We've got alpha for live snow, dead loads, and the resistance factor phi for our resistance. And this is equal to the bias in the load effects divided by the bias in the resistance multiplied by e to the power of our reliability index times the total variance between these two random normal variables. So you don't need to follow that process, but what you do need to know is that when we factor down the resistance, that should be greater than or equal to the increased load effects. The ratio of those two values is basically set based on the reliability index. For example, the bigger beta is, either alpha needs to go up or phi needs to go down, right? So we need a bigger spread between the load effects and the resistance. If you wanted to calculate a factor of safety, probably in mechanics, did you talk about factor of safety in mechanics and materials? I'm sure it's like factor of safety is 1.5 or 2, or in soils and foundations, you always talk about factor of safety, right? You don't do limit states design for foundations. Probably haven't gotten there yet. Factor of safety is basically this ratio. And historically, we would have just used a factor of safety. And that would be easy because we know our load statistics, we know our liability index, and then we just know what our factor of safety is. The problem is when we have more dead load than live load, the factor of safety is too big. If we have more live load than dead load, the factor of safety is too small. And so this summation here of the load effects with their individual load factors tries to solve that problem by accounting for the fact that, for example, live load might have more variability, and so we're going to have a bigger factor on live load compared to dead load. We're going to use a slightly smaller factor for that one. On the quiz, I think I asked you to figure out what the factor of safety might be if you're trying to design something from scratch for a certain value of beta. And so basically, you should see here that factor of safety being equal to this makes these two expressions more or less equivalent. Okay. Here we're going to have different load factors for dead, live, snow, and wind load. We're going to have different effects, dead, live, snow, and wind. And then there's going to be a resistance factor for whatever it is we're considering, yielding of a brace, fracture of a bolt. We're going to have different resistance factors for the nominal resistance that we would typically calculate. Okay, does anyone have any questions about what our goal is here in terms of making sure the factored resistance exceeds the factored load effects? What this reliability index beta is for, or why this might result in different load factors for the different kinds of load effects we're considering acting on our structure. Okay. We basically get our load effects from the building code. And so we've got dead, live, snow, wind, and earthquake loads that we've already talked about. We're going to figure out now how we add these together, right? So we're going to have a load factor on dead, load factor on live, snow, and wind. And we add these load effects together in different ways, depending on what is most likely to happen. Now, we do want to make sure that we have an acceptably small probability of failure, and that's something a little bit less than the probability of dying by choking on your own food, or a little bit more depending on the limit state we're considering. Do you think we should just say, okay, well, the worst thing that could happen with my dead loads is going to happen at the same time as the worst thing that can happen with my live loads, at the same time as the worst thing that can happen with my snow loads, at the same time as the worst thing that can happen with my wind loads, at the same time the worst thing that can happen with my earthquake? Should I be adding all of these things together? Why or why not? Is it likely I'm going to get the 1 in 50-year windstorm at the same time I get the 1 in 50-year snow load, at the same time I have an unusually large occupancy in my structure? It's not likely, right? And so in addition to calibrating these load factors, we also have to determine how we're going to actually add these effects together. And so what the building code tells us is from time to time, have to consider the worst case for certain loads. And so when we're designing for ultimate limit states, we might take 1.25 times the dead load. That implies here that alpha dead is 1.25. At the same time that we have 1.5 times the live load. Alpha L is 1.5. And so that's one load case we're going to check. And at the same time, we might just add 1 times the wind load, the snow load, or 40% of the wind load. And this depends on a bunch of stuff. When is wind most likely to occur at the same time as snow? When is all that likely to occur at the same time as your worst case wind? And so basically how this works is we've got a load case number 2, which is dead and live, plus snow or wind. We have a load case 3, which is basically dead and snow, plus live or wind. We have dead and wind, plus live or snow. And then earthquake, and because they're quite rare, plus half live or 0.25 times the snow load. Okay, so this might look a little bit weird. How do I use these companion loads? When do I add them into the principal loads? Basically, each of these load cases is going to have several different subcases. I don't really like how it's presented here, but I guess it's brief. Basically, how this works is, if I'm looking at the first principal load case, there's nothing else. 1.4 times the dead load, just in case I've got a lot of dead load and it happens to be extremely rare that exceed what I calculated. I'm going to use 1.4, but all these other ones have a bunch of different combinations. And so, for example, load case 2, we might have the 1.25 times the live load, or dead load plus 1.5 times the live. We might have that plus snow. We might have that plus wind. And then there's also a case here where we might reduce the effects of the dead load. Can anyone think of a situation where we might reduce the effects of the dead load in our structure? That seems weird. Like, let's reduce the amount of weight of our building. It means let's underestimate the load of our building just in case something bad might happen if we do that. What might happen if we calculate a dead load and the weight of the building's less? Is there anything that could happen to our structure in that situation? What if wind is blowing on our structure? A simple case might be we've got wind blowing on our structure, and we basically more or less have a certain weight of the structure that's holding it down. And this isn't necessarily a consideration we're going to talk about in this class, but there is a geotechnical consideration that you're thinking about currently in foundations. Preventing overturning, right? We want to prevent overturning of our structure with a certain amount of, with a certain acceptable probability of that happening. If we overestimate the weight of the structure, but it's less, what's likely to happen to our building when wind's blowing on it if it's too late? Well, it's going to blow over, right? You've got a turning point here. The only thing preventing the wind from blowing your structure over is the restoring overturning moment that comes from the weight of the structure. And so in that case, we're going to neglect live and snow load, and we're also going to reduce the dead load to account for the fact that we might have overestimated it. Okay, we're not going to see that case very much in this class, but it's something that you do need to be aware of. We've got all the other ones, snow as well, and basically you can kind of crunch them all out yourself. Certain ones are going to apply more to certain members. And so, for example, we might have more wind load affecting a brace than we have gravity load. And so the way this works is we calculate the effects from each of these members or each of these loads on specific parts of our structure. And so, for example, if we look at our roof joists, we're not going to have a roof live load if the snow load exceeds it. So generally, we're just going to have snow and dead load. That simplifies load combinations. We don't need to include wind or earthquake for that. Floor joists, there's not going to be any wind on them, well, it could be vertical earthquake. We're not going to talk about that, but there's certainly not going to be any snow on internal floor joists. So we've got live and dead loads to consider. This does start to get a little bit tricky when we have braces. So we might have a brace down here that's designed for wind load, and then we have to consider the notional lateral load effects. So we're going to have a dead load tension, a live load tension, a snow load tension, and a wind load tension. And it's not the load applied to the structure that we apply the factors to. It's the force in the member, T, for example, T live, T from snow, T from wind. There's a tension on that member from these different loads. We're going to calculate them using the specified loads that we calculate. Then we're going to add those effects together using the load combinations. Okay? You'll have a question, or you'll have an opportunity to ask me a question after I go through this with you. In the lecture 6, for example, we're looking at the compression on a column that might come from snow roof live, and dead load. And we calculated these values, 244 kilonewtons for snow, 286 reduced live, 79 roof live minimum, and a dead load of 1,355. We'll see if this pull everywhere works. With the information that we just discussed, primarily between these load combinations and what they mean for us in terms of how we might actually apply them, which of the load combinations that we have shown here might maximize the total factored compression force that we would have acting on that column? How are we going to apply the load combination that generates the largest possible factored compression force on that column that would be reasonable for us to design that column for? We've got a compression from dead, live, roof live, and snow, and perhaps there's tension from maybe some wind load acting on the roof. How do we add those together so that we can determine what the maximum likely load will be in extremely rare case, so that we can make sure the column has enough strength? Pardon me. I love the crowd effect here. We kind of have some answers piling up more or less on one of these combinations. So any of these combinations are potential ones that we might consider. There are, there's plenty of combinations. We've got 1 plus 6 plus 6 plus 6 plus 2. So that's 18 plus 2 plus 21 load combinations here. We can immediately get rid of earthquake, right? Because there's not a significant amount of earthquake load acting on this column based on what we've calculated. It's an interior column, so we're not going to have significant earthquake loads anyway. And so obviously these ones aren't going to apply for us here. We've got wind load. Why are we not considering wind load in our load combination perhaps? No, that wouldn't be why. It's still generating a column and if so, this one comes, if you looked at the example lecture notes, like we do have the potential for an uplifting wind suction on the roof, right? And so it is possible that the wind is going to be at the roof level pulling up on that column, okay? So go look at the example lecture notes from lecture 7. We have a suction on the roof that might pull that column up. Why would we not include that in the calculation of the load, the maximum load effect? Is it making the compression on the column more or less? It's pulling up on the column, right? So if wind is actually pulling up on the roof and that comes with the column, that's going to be taking away from the compression on the column. We don't want that. We want to maximize the total compressive force acting on that column. So we're not going to include any of these wind load effects either. That also means we're not going to try this or this or this or this, because that's reducing the total compression acting on my column. That leaves me primarily with different dead load and live load and snow load combinations. Now we've got a bunch of different ones to consider. We're obviously not going to ignore the snow or live because that's going to add. So we do want to add everything together. We're certainly not going to reduce the dead load. That's not adding to the compression on our column. Ultimately, this comes down to, are we going to put the bigger factor on the snow load force, or are we going to put the bigger factor on the live load force? Those of you who picked answer A, why did you choose that instead of answer B? Does anyone feel comfortable sharing? Well, we can either put the bigger factor on the live load or the bigger factor on the snow load. The bigger number is the live load value here. So generally, if we're designing for snow, if we're including snow in these load combinations, we're not going to include the minimum roof live load. But 286 is bigger than 244. 1.5 times 286 versus 1 times 286, right? We're going to put the bigger factor on the bigger force here. And so ultimately what we're going to do is have 1.25 times dead to maximize that dead load effect, And then we're going to put the 1.5 on the live load column force and the 1 on the snow load column force. Okay, so we're going to do 1.25 times dead plus 1.5 times live plus 1.0 times the snow load. And I'll do that quickly here just to give us a sense for what this might look like. Did anyone calculate that value, or did you just figure it out from process of elimination? Did anyone calculate this? If I was to say the number? No. I get a value of 2,367 kilonewtons. How I'm going to denote that is I'm going to use C subscript F. Subscript F means factored. I've applied my NBC load combinations to get the maximum factored column force from the loads present on the column, including that uplift that we might get from the roof level. So my factored compression on my column that I'm going to make sure the column is strong enough to resist is almost 2,400 kilonewtons. Okay, so we went through this example in lecture 6 of calculating the individual load effects on the column. In lecture 7 example notes, there's just a quick calculation for the uplift on the column. It's not critical for us here. Today, we're talking about how to add these things together such that we're less likely to underestimate the load effects when we're designing our member to resist this force. We're going to come back to this force later on in like lecture 20 something when we start talking about the design of compression members. But it's important that after today you take away how to do this addition of the load effects for an example force. This is just a column. It could be the moment for a beam, the shear in a beam, the tension in a brace. It's important that you can navigate through these tables of load factors, determine which ones are most likely to be most critical, and figure out from there which ones to consider. If you're not comfortable figuring out which ones will work by process of elimination, the easiest thing to do is just literally crunch out the load combinations for everything and pick the biggest number. Okay, if you cannot go through the table and say, okay, wind load's not going to be important here, I'm not going to reduce the dead load effects, I'm not going to consider earthquake, just plug in the compression for your 4 members in all of these load combinations, and what you want to take away as your factored compression force is the maximum compression acting on that column. Are there any questions about what the load factors are intended to do, why the load factors are presented in the way they are in the building code, and how we add different loads together, and how that applies in this case to the loads that we calculated previously on the column to get the factored compression we're going to ultimately design that member for? Okay. So the resistance factors tend to look something like this. We'll see these as we start going through the different members and connections for the rest of the course. For example, we're going to see next day that if we're looking at the ductile failure of steel members, like yielding of a brace, the target reliability index is 3, more likely to get warning from yielding in a ductile manner that provides warning for egress. So we'll use a slightly bigger resistance factor. Compared to localized fracture of the steel members, fracture of bolts or of welds, we tend to use a higher reliability index to make them less likely to occur. We want our structures ultimately to fail in a ductile manner if they ever are going to fail, and so we make the ductile failure mechanisms more likely to happen by using a smaller reliability index and a larger resistance factor. We'll talk about those more in all of the remaining lectures, the rest of the course. What I want to talk about briefly before we wrap things up is serviceability limit states. And basically, serviceability limit states are those that restrict the intended use and occupancy of the building. And they include deflection, excessive vibration, permanent settlement, usually in a kind of a differential settlement behavior, or local structural damage like cracking. Cracking of walls prevents doors and windows from opening. Excessive deflection of beams tends to delaminate floor tiles or crack floor systems, and bouncy floors are just annoying. We want to prevent those kinds of things from happening. Are you more likely to be upset if you're bouncing on the floor while you walk on it, or if the floor above you falls on your head and crushes you? What are you more likely to be upset about? technically the bouncy floor, because you won't be able to feel frustration with being dead, right? But you're probably, if you were critically injured, you'd be not very happy about that. Your loved ones certainly wouldn't be very happy about that either. But that's tongue-in-cheek. And what I'm trying to communicate here is we're applying load factors to things we want to have happen in the absolute rare circumstances, which is death or injury or significant injury. Other things, cracking of floors or walls, not very important, right? So we're going to accept the fact that those are going to happen more frequently because they're more maintenance issues than they are personal injury issues. In that light, what we're going to do is we're going to use different load combinations. So for example, later on in this course, we're going to be taking the deflection that we calculated from dead load or snow load or live load, and we're going to make sure that they're less than allowable limits. But we're not going to bump up the load effects to make sure that it's a really rare occurrence. We're just going to make sure that the deflection that's acceptable, that causes cracking, is more or less what we calculate it to be. In this case, we're basically going to calculate a deflection that might look like this, and we're going to calculate a load effect that might look something like this. And our goal here is more or less for the expected values for both those curves to be in alignment. What does that mean in terms of the probability we expect these kinds of things to happen with? If the two mean values line up with each other, what does that mean in terms of a z-score? Well, if we subtract these two random variables, then we're basically going to get a new curve where the mean sits here. We've got half the curve over here, half the curve over here. Z is 0. What does that mean about the probability that these things are going to happen? It's like a 50-50 chance, right? It's 50-50 chance that a wall is going to crack or a floor is going to be too bouncy in the lifetime of a building. And that's more acceptable to us than death by crushing from the floor falling onto us from above. Okay, so slightly different load factors. They work in a similar way. We're going to be looking primarily at mostly live and snow load type deflections. We might also be looking at wind load deflections. For example, we want to make sure the building doesn't get pushed too far to the side from the wind so that the pretty stuff on the outside doesn't start to crack and fall off. And so primarily how this is going to play out for us is in terms of maximum deflections, either lateral or vertical. Okay, so trusses will get pushed to the right, so the building will get pushed to the right. We don't want the pretty stuff on the outside to crack and fall off, so we're going to put a limit on that deflection. We don't want our beams to sag down too much under the snow or live, otherwise the floor is going to crack. That's not something we want to have to deal with all the time, but these things are more acceptable to us than failure of a structural member. Does anyone have any questions about ultimate limit states versus serviceability limit states, how we might differentiate between what they are, and when we would apply these load factors versus the other ones for ultimate limit states design? Cool? All right. Basically, now you should be able to define and differentiate between ultimate limit states, failure that can cause collapse and serious personal injury, versus serviceability limit states, things that are annoying. We want things that are annoying to happen more often than things that are going to kill or seriously injure us. And so we have different load factors that represent different reliability indices. To be able to discuss the statistical principles used to provide that structural reliability, think about things in terms of reliability index. Usually that's a value that we define based on an acceptable probability. And using that index, you should be able to calculate, for example, a margin of safety that would be acceptable based on the statistics of the load and resistance. And finally, you should be able to find and apply, most importantly, nothing is more important than this and this. What is ultimate limit states? Where are those factored load effects going to come from? And can you apply those load combinations to get that maximum factored effect acting on these structural members? Does anyone have any questions about these three learning objectives, why they're important, or any of the other stuff that we talked about in lecture this morning? Easy enough. Enjoy the rest of your day, and we'll see you all Friday morning.